The second type of induction problem that we see in extension 1 are these divisibility type problems. So we're no longer looking at a series. We're just going to prove that n times n plus 1 times n plus 2 is divisible by 3. Now, yeah, logically it makes sense. If you've got 3 consecutive numbers and you're multiplying together, well, one of those numbers must be divisible by 3 in itself. So of course the whole product's going to be divisible by 3. But that's not good enough for a proof though. Let's do it via induction. So again, we will prove it true for n equals 1, but this time I don't have a left-hand side equals right-hand side thing. All I really need to do is substitute in, so 1 times 2 times 3, well that's 6, and just confirm, well yeah, 6 is divisible by 3. Okay, so it's true for the first case, true for n equals 1. Now here's the next interesting thing. We're going to make an assumption. But again, how do you write an assumption down and just say, oh, is divisible by 3? Well, what we do is we create a left-hand side and a right-hand side. So the left-hand side is what we're trying to prove, n times n plus 1 times n plus 2, but we've replaced it with k, and we're saying we want it to be divisible by 3. So how we can express that is that's equal to 3 times something. But that thing has to be a whole number for it to be divisible by 3. So I've called it p, equals 3p, where p is an integer, so an element of the z, so the set of integers. That's going to be my assumption. I now need to prove it for the next case. So n equals k plus 1. So everywhere I've had my k, I'm now going to change to k plus 1. So the next set of 3 consecutive integers would be k plus 1, k plus 2, k plus 3. That also has to equal 3 times something. But it's not going to be the same thing, so I just pick another letter. Well, Q's the next letter, so 3Q, and again Q has to be an integer. Let's do the proof. So I've got k plus 1, k plus 2, k plus 3. I've got to get my assumption in there somehow. See, this is not like the series one where I can go, oh, now I'll write it with the second last term and wonderful, there's my assumption. So how do I get my assumption into this one? Well, it comes down to that extra, let's call it a term for want of a better word, that we've got there. The assumption didn't have k plus 3 in it. So I'm going to expand out, but not completely. All I'm doing is breaking up the k plus 3. So I've got k lots of k plus 1, k plus 2, and 3 lots of k plus 1, k plus 2. But now look at that first term, k plus 1, k plus 2. That was our assumption. Now I can get the assumption in there. That's going to be 3p, whatever p happens to be, that thing we said was just some integer, plus 3 k plus 1, k plus 2. We've got a common factor of 3. And that's what we were looking for. We wanted to show it was 3 times something. So it is 3 times something, but remember that thing had to be an integer. Is this an integer? I'm claiming, well, yeah, it is, because 3q, where q happens to be for our one, p plus k plus 1 times k plus 2, but remember we defined all these things. We said p was an integer. We said that. We also said k was an integer. If you break it down, if k is an integer, well, k plus 1's got to be an integer, and k plus 2's got to be an integer. And when you multiply 2 integers together, you get an integer. And then when you add that to p, which is an integer, so yes, q is an integer. It does belong to that set of integers that we call z. So we have our proof. Concluded, remember it's only good if my assumption's good. So hence the result's true for n equals k plus 1 if it's also true for k. And then tie it all together. Well, hang on, we went and showed it was true for n equals 1. Therefore it's got to be true for 1 plus 1, which is 2, and 2 plus 1. And we can induce all of the integers by induction. Let's do another one. 3 to the power of 3n plus 2 to the power of n plus 2. And our claim here is that this is going to be divisible by 5. It'll always be divisible by 5. Well, let's check out the first case. N equals 1. We'll get 3 to the power of 3 plus 2 to the power of 3 as well. That's 35. 35 is divisible by 5. It works for 1. It's true for 1. I'll assume for n equals k, k being some positive integer. Notice in this case I need it to be a positive integer, because if it wasn't a positive integer I'd get a negative index and that would create a fraction, and this fraction is not going to be divisible by 5. So I have to assume it's a positive integer in this case. Okay, 3 to the power of 3k plus 2 to the power of k plus 2 is 5p, where p is some integer. Next case then would be, everywhere I see k, replace it with k plus 1. So 3 to the power of 3k plus 3 plus 2 to the power of k plus 3 will be 5 times something. Let's just call it q. Proof. How am I going to get my assumption into this one? What I do is I break up one of those two terms. Doesn't really matter which one. But I need to have something there that was in the assumption. And if you go back and have a look at the assumption, I had two things in there. 3 to the power of 3k, and I also had 2 to the power of k plus 2. I need to create one of those things to allow me to substitute in. See, I can always rearrange my assumption and make the 3 to the power of 3k the subject. And instead of just substituting in 5p, I'll substitute in 5p minus 2 to the power of k plus 2. So I can still get it in there. But I need to get one of these two things. So alright, let's go back to it. I decided I'm going to use the 3. So I've split that up. 3 to the power of 3k times 3 to the power of 3. That's our index laws. We add the powers, we multiply. And of course 3 cubes 27. So I can say that's 27 times 3 to the power of 3k. That now allows me to put the assumption in there. Over on the right, you'll notice I didn't just say by assumption, because here it's just not immediately obvious I've used the assumption because I've rearranged it. So I've really highlighted what I've done. I've said, hang on a sec. No, I know 3 to the power of 3k is equal to 5p minus 2 to the power of k plus 2 by the assumption. So letting people know, yeah, I've used the assumption, I just rearranged it so I could get it in there. Let's now play with what we've got. Remember, we're trying to show that there is a common factor of 5 in all this. I'm now going to expand out, collect like terms, and hopefully I'll get it. 27 times 5, well that's 135. I've then got 27 lots of 2 to the power of k plus 2, but I've also got this 2 to the power of k plus 3. But of course 2 to the power of k plus 2 and 2 to the power of k plus 3 also have a common factor. They're both 2 to the power of something. And when we factorise, we take out 2, well in this case 2 to the power of whatever the lowest power is. Now if I make them both 2 to the power of k plus 2, well, the 2 to the power of k plus 3 then would become 2 times that. So have a look at what we've got. We've got minus 27 lots of 2 to the power of k plus 2, but we've also now got plus 2 lots of. We'll pull that together, that's negative 25. We now have two terms there. Both of them have a factor of 5 in them. So I can pull out that factor of 5. The only thing we have to make sure of now is what we're multiplying by is an integer. Okay, so I'm claiming, yes, that's 5q, where q is equal to this, and I reckon it is an integer. Well, let's look at it. P we define to be an integer, so yeah, 27 times p will be an integer. Well, what about this thing here? 2 to the power of k plus 2. Well, it is an integer, because remember, in my assumption, I said it belonged to the positive integers. Now, if I just said it was an integer, 2 to the power of k plus 2 would not necessarily be an integer, because I could get a negative power. That's why in my assumption I needed to make it a positive integer for the proof to work. But it does work for what we've done. So hence it's true for n equals k plus 1 if it's true for k. We know it's true for the first case, so now we can induce it true for all of the integers. A little bit of manipulation in that type of one. Let's do something a bit different. Let's do polynomials and use that same idea. So we're going to prove x to the power of 2n plus 1 plus a to the power of 2n plus 1 is always divisible by x plus a. X plus a. Well, let's see what happens when n is 1. I get x cubed plus a cubed. We've got a formula for that. That's the sum of two cubes. That'll be x plus a, x squared minus ax plus a squared. Well, yeah, we have a factor of x plus a. So that is divisible by x plus a. Works for the first case. Assume it true. Again, I'm making k a positive integer. Remember, basically match what they've said in the question. See how they've said prove it for positive integers? So I've said, well, k, I'm going to make it a positive integer. Make sure you write the words down, because in those divisibility ones, we normally say times p or q or whatever, where p or q is an integer. But we're not dealing with integers here. We're now dealing with polynomials. So I'm defining qx to just be a polynomial. It doesn't necessarily have to be an integer in this case. As long as x plus a is a factor of this polynomial, we're okay. And we're going to prove another polynomial, tx. We want to prove x to the power of 2k plus 3 plus a to the power of 2k plus 3 is x plus a times some polynomial. Okay, let's do our proof. Remember, I've got to try and get my assumption into this x to the 2k plus 3 plus a to the 2k plus 3. So I'm using the same idea that I did for the numbers. I look at my assumption and I say, look, I've got two things here. I'm going to have to substitute in for one of those things. So I need to create x to the power of 2k plus 1 or a to the power of 2k plus 1. As long as I've got that, I can sub the assumption in. So I've split the x term up. So I've said that's x squared times x to the 2k plus 1. I've now got a spot I can put the assumption into. So let's put it in there. This time I've just said by the assumption rearranged. Now when I expand that one out, I've got x plus a. Remember, we're trying to show x plus a as a factor. Well, it's certainly a factor of x plus a, x squared qx. Can I get x plus a out of the other two terms? I've got minus a to the 2k plus 1 x squared plus a to the 2k plus 1 a squared. Well, there is a common factor there. That common factor is a to the 2k plus 1. Now if I factorise out the negative factor, I'm left with x squared minus a squared. But, of course, x squared minus a squared, difference of two squares. So I could rewrite that as x minus a, x plus a. Aha! I've now got this common factor of x plus a that I was looking for. Let's pull that out, and it is times something. The question here is, I don't have to say this is an integer. All I need to confirm in this case is that's a polynomial. Remember, we're just trying to show it's x plus a times some polynomial. And yeah, it is. Because our definition of polynomial is we just had all these terms. So long as the power is a positive integer, we know it's a polynomial. Let's have a look at our powers. Well, 2k plus 1, remember we defined k to be a positive number, so 2k plus 1 must be a positive number as well, because if you double it and then add 1, you're not going negative, it's going to stay positive. So that is a polynomial. So yeah, it does work. Hence it's true for k plus 1 if it's true for k, and now we can induce again. Now where n equals 1, therefore it's going to be true for all n, all values of n that are positive integers by induction. Okay, so those are divisibility types of induction questions. Pretty much that's all we'll see in extension 1 is one of those two types of inductions. They might vary it a little bit, but pretty much it'll come down to one of those two types.